And welcome to Activity 11. We have made it all the way to Activity 11. And the title of Activity 11 is Congruence, Transformations, and Triangle Congruence. So I don't know if you've ever noticed, but I thought this was pretty funny. The title of lesson 11-1 is called Trust Your Judgment or Trust Your Judgment. And you'll see why they use this term trust here for the title. So lesson 11-1 is all about congruent triangles. We are going to focus heavily on triangles. We start with triangles because, in fact, all shapes are made up of triangles. So if we can focus in on the triangle, we can start to uncover more truths about the other shapes as we move through the year. So as always, let's look at our learning targets. We will use the fact that congruent triangles have congruent corresponding parts. And if you're still not understanding what that term corresponding means, not just with parallel lines, but if you're still having trouble with corresponding parts, we'll see that here in our text. We will also determine unknown angle measures or side lengths in congruent triangles. So let's take a look at our text. Just take a moment, pause the video, read through the text before continuing. So hopefully you've kind of uncovered the scenario here. Greg Carpenter, what a great name, works for a green construction company. The company is building a new rec hall, and the roof of the hall will be supported by what's called triangular trusses. If you're not sure what a triangular truss is, I kind of pulled up some images here. So triangles are actually used all over construction because they are one of the most solid shapes that there are, one of the most stable shapes that there are. And in fact, all shapes are made up of triangles. So it makes sense here. This is what triangle trusses look like. These are just samples of how they're used, often in bridge work, as you see here, but definitely the halls or the roof structure. If you actually ever go up in your attic, you'll probably more than likely see nothing but triangles because it is such a strong structure. That's why we're going to be looking at the triangle here. Triangles are often used in construction for roof and floors because of their strength and rigidity. I thought that was interesting that they use the term rigidity when we've been studying rigid motions. Each angle of a triangle is held solidly in place by its opposite side. So that's what makes that structure so strong is this opposite side right here holds together its opposite angle. So each of the trusses contains pairs of congruent triangles, and Greg's boss tells him that his first job will be to determine the side lengths and angle measures. Well, just like just any normal person, Greg starts to think, do I really have to measure every single side and every single angle of these trusses? Work smarter, not harder, right? So let's continue on in our text. Greg wonders if I know that two triangles are congruent and I know the side lengths and angle measures in one triangle, do I really have to measure all the sides and angles in the other triangle? So we know that congruent figures, or in this case, congruent triangles, are going to have the same size and shape. So Greg's already thinking there's got to be a shortcut, right? If I know the measures of side lengths and angles of one triangle, do I have to measure all the sides and angles in another? So with that in mind, if you would, go ahead and draw a line under number 3. See if you can complete 1 through 3 on your own before playing through the video. So hopefully you've taken a second to complete this on your own. But Greg begins by examining the two triangles from a truss. So he has gone back and chosen 2 of these triangles specifically to examine. And it says, according to the manufacturer, the 2 triangles are congruent. So if the 2 triangles are in fact congruent, then we should be able to find a series, or in this case, just one rigid motion that maps one onto the other. So number 1, because the 2 triangles are congruent, can one triangle be mapped onto the other? Yes, if the 2 triangles are congruent, then a series of rigid motions, or in this case, one rigid motion, can show the 2 triangles are congruent. If you look at the diagram here, I thought the easiest possible route was a line of reflection halfway between points C and F. such that triangle ABC map to triangle DEF specifically. So I thought, simply put, a line of reflection here would map this triangle ABC onto triangle DEF. So number 2 says, suppose you use a sequence of rigid motions, or one above, to map triangle ABC to DEF. Find the image of each of the following under this sequence of transformations. So in other words, where will A map to, or point A map to, after the reflection? Where will point B map to, or where will line segment AB map to under this reflection? So notice I wrote over here, order does matter. Line segment AB maps to line segment DE. And you might be asking yourself, or telling yourself, line segment AB is probably the same length as line segment DE, but why did I mention line not ED? Because if we're talking about specifically mapping one triangle into the other, point A maps specifically to point D. I know line segment DE and line segment ED are the same, are two different names for the same segment, but when we talk about mapping, order matters. We're talking specifically that point A maps to point D and point B maps to point E. So that's why I said line segment DE and not line segment ED. So if you notice, I use this color coding hopefully to give you some insight on these images under the transformation. Let's look at item 3. What is the relationship between line segment AB and line segment DE? And what is the relationship between angle B and angle E? Well, we can suggest, knowing that these two triangles are congruent, and if there is a rigid motion that maps triangle ABC onto DEF, then these corresponding parts, line segment AB and line segment DE, they have to be congruent, because it is a rigid motion, or is a series of rigid motions, which doesn't change size or shape. So if we know these two triangles are congruent, and there's a series of rigid motions that can show that, then line segment AB has to be congruent specifically to line segment DE. Therefore, angle B, whatever measure angle B is, angle E has to be the same measure. That's what's stated here. And we're coming to this point in our text where we're really trying to focus on what you see highlighted here. So take a moment, if you would, pause the video, read through this text, highlight some important things before continuing on. So this is some very important text right here. Hopefully you took a second to read it over as I highlighted some things. Incongruent triangles, corresponding pairs of sides are congruent. That's what we saw here. Corresponding pairs of sides are congruent. And corresponding pairs of angles are also congruent. As we said here, in that case, angle B and E were congruent. So it said, when you write a congruence statement, that's what this is referred to as, you write the vertices so that corresponding parts are in the same order. That's why I tried to go and emphasize back here that order does matter. If you notice, I actually called this congruency statement, I call it the drop the mic statement. You know what happens when someone's on stage and they drop the mic? It's because they've said all that they need to say and it's time to get off the stage. So when we write that triangle ABC is congruent specifically to triangle DEF, we're actually saying all of these congruency statements. And it's based on the order, such that if you look in the original statement, AB being the first 2 points in the triangle, or listed in the triangle, those are congruent to line segment DE. And BC, line segment BC, is congruent to EF, and so forth and so on. So the reason I call it drop the mic is that if we can write this statement, it tells us all of this other information. In fact, it tells us that there are 3 pairs of sides, 3 pairs of congruent sides, and 3 pairs of congruent angles. So this statement is very important, not only that the order matters, but that we have that statement to uncover which corresponding parts are congruent between 2 different triangles. So with all that in mind, let's take a look at example A. For the truss shown below, Greg knows that triangle JKL is congruent to triangle MNP. So there is that drop the mic statement. So with that statement, we know that line segment JK is congruent to line segment MN. We also know that angle N, or I guess I could say angle K, is congruent to angle N. So we know 3 pairs of corresponding sides are congruent in these triangles, and 3 pairs of corresponding angles are congruent in these 2 triangles. And that's what this text is telling us here. So let's get back at it. Sorry for that, kind of lost. I was pulled away for just a moment. But so we're making a pretty big claim here that if these 2 triangles are congruent, then corresponding parts are congruent as well. So triangle JKL being congruent to triangle MNP, corresponding part line segment KL is congruent to NP. So if we know the measure of KL, we know the measure of NP because of our previous definition of congruency. For 2 figures that are congruent, they have the same measure. So if KL is equal to NP, and KL, they show us in the diagram, is 2.1 meters, NP is also 2.1 meters. So we're suggesting something really intense here when we make that statement that these 2 triangles are congruent. So now what I would like for you to do with that in mind, go ahead and draw a line at the bottom of your page, enough to hopefully explain item E, but try these parts A through E before continuing with the video. Okay, so hopefully you took this opportunity to try to figure out this on your own. Remember, this statement, this congruency statement, is very, very important. When we make the claim that 2 triangles are congruent using this statement, we're really saying all of this information here, that angle R is congruent to angle X, angle S is congruent to angle Y, angle T is congruent to angle Z, and all of these pairs of corresponding sides are congruent as well. That's all found in this statement because the order matters. So we know that congruent angles, congruent sides, they have the same measure. So it says find each of the following if possible. It's just based on what's given here. So don't get hung up on this idea if possible if it's not making sense to you. So A asks for the measure of angle X. Well, we know the measure of angle X is equal to the measure of angle R. So if we don't have a measure for angle X on this triangle, and we look to a congruent triangle and its corresponding angle R, and we also don't see a measurement, we're just going to put a question mark there and say it's not possible to know the measure of angle X or R simply because we don't know the measure of angle R. But let's look at item B. Hopefully that makes a little bit more sense. We're asked to find the length of YZ. Well, we look at this triangle and we don't know the measurement, but we know that YZ is the same length as ST because of this statement, and they tell us that the length of ST is 15 centimeters. So the length of YZ has to be 15 centimeters as well. This is the transitive property if you really want to look at it that way. If YZ is equal to ST and ST is equal to 15 centimeters, then YZ is 15 centimeters. Part C, the measure of angle T, we look at triangle RST and we see we don't have a measurement for angle T. So we look at its corresponding angle in triangle XYZ, which is angle Z, and we see that the measure of angle Z is 47 degrees. So if the measure of angle T is equal to the measure of angle Z, then angle T is 47 degrees. Last but not least, part D, we know the length of XZ is the same as RT. It's equal to RT, but we don't know the measure of RT or XZ, so we simply say it's not possible to know the measure of XZ, although we did point out that it is equivalent to the length of RT. Last one on try these A. Part E says both triangle JKL and MNP are equilateral triangles. Do you think that's important? Yes, in which the measure of each angle is 60 degrees. So just let's break that down. An equilateral triangle, all sides are congruent, all 3 sides, and all 3 angles are congruent. And the reason we know that all equilateral triangles will have 60-degree angle measures is because an angle, the sum of all 3 angles in an equilateral triangle, I should probably put that, sum of angles is 180 degrees. And if all 3 are equal, we divide 180 by 3. So all of the angles in an equilateral triangle are 60 degrees, which starts to make you think, can you tell whether or not they're congruent? Well, their corresponding angles might be congruent. In fact, if all 3 angles of this triangle are 60 degrees, and all three angles of this triangle is 60 degrees, it definitely leads you to believe that they would be congruent triangles. But in order for triangles to be congruent, corresponding angles have to be congruent, but corresponding sides also have to be congruent. So I said no, corresponding angles are congruent, yes, but corresponding sides don't have to be congruent. In fact, triangle JKL can still have all three angles 60 degrees, but its side measures can be 5 meters. Or MNP, all of its angles can be 60 degrees, but its side lengths can be 3 meters. And there's actually a non-rigid motion that helps verify why this can work out, where two equilateral triangles don't necessarily have to have the same side lengths. So keep that in mind. Just because we know angle measures does not mean that two triangles are congruent. So that is the end of 11-1. We're seeing how congruent triangles can be proven by a series of rigid motions. And then we're seeing how congruent triangles can help us find missing measurements on one of those two triangles that we're saying congruent. So as always, go back to your learning target, reevaluate, rank your understanding of this material, and watch and re-watch the video, any section you need to, and reach out to me if you have any other questions. The last thing I'll leave you with, a little bonus question. The first one that can text me on Remind that answers this question: what non-rigid motion proves that two equilateral triangles can have the same angle measures, but not necessarily the same side lengths? So what non-rigid motion can actually prove that two equilateral triangles can have the same angle measures, so the angles are preserved, but the side lengths do not have to be congruent? So reach out to me when you think you know the answer. And as always, thank y'all for watching.